All right, guys, Dr. Colbreth here with chapter 14, number 49. It says the two blocks in the figure oscillate on a frictionless surface with a period of 1.5 seconds. So this bottom surface down here is frictionless, and these two blocks oscillate back and forth. The upper block just begins to slip when the amplitude is increased to 40 centimeters. What is the coefficient of static friction between the two blocks? All right, so there's friction between this upper block and the lower block, and as the blocks oscillate, it's this friction that moves the upper block to the right and moves the upper block to the left. But at some point, the acceleration of the oscillation becomes too great, and the static friction cannot provide the required force to move the upper block with the lower block, and so it slips. So since we're dealing with static friction here, this is a clue that we need to use dynamics and Newton's laws to analyze these forces so we can apply our static friction force model. So let's start with a free body diagram of the upper block. What forces do we have acting on that upper block? We have the force of gravity, which points down, the normal force, which points up, and I'm going to consider when the two-block assembly is moving to the right, in which case it is the static friction force on this upper block that moves it to the right. And that is all of our forces acting on the block. So we've completed our free body diagram. The next step is to sum the forces. I'm going to start in the y direction. The sum of the forces in the y direction is plus n minus the force of gravity, which I'm going to write as mg, is equal to the mass times the acceleration in the y direction. Now we're considering oscillations in the x direction, but there's no motion in the y direction, so our acceleration in the y direction is equal to 0. So that gives us that the normal force is equal to mg. Now we can repeat this process in the x direction. The sum of the forces in the x direction, we have just our static friction force Fs, and that's what gives us our acceleration in the x direction. On the right-hand side, we have that equal to m times a. All right. Now we want to consider the situation just when the block begins to slip. So the static friction force, as you may recall, can have a range of values from 0 up into a maximum value. And above the maximum value, the static friction force gives way and it slips. So at this slipping point, our static friction force is equal to that maximum value, and Fs max is given by the coefficient of static friction μs times the normal force n. And we can substitute that into this upper equation here, and we get μs times n is equal to the mass times the maximum acceleration, maximum allowed acceleration in the x direction. And this expression, we can substitute in mg for n, because we solved for that up here, doing the sum of the forces in the y direction. We're going to get μs times mg is equal to the mass times the acceleration, the maximum acceleration in the x direction. Our masses cancel. We'll get that μs is equal to ax max divided by g. I'm going to call that equation 1. All right, so we sort of come to the end of the line with Newton's laws here, and we found that for our maximum allowable acceleration, ax max, once we've calculated that, we can get a value for the coefficient of static friction. But how are we going to figure out what the maximum acceleration is when we have an oscillation of amplitude 40 centimeters? Well, we're going to need to use our oscillation kinematics for that. Now, we're going to have to sort of push the kinematic equation further than we did in class. So let's go ahead and start with the position equation. We get that the position at time t is equal to the amplitude times the cosine of omega t plus the initial phase, phi 0. And we need to move down the kinematic ladder to the acceleration. So starting with the position, if we want the velocity, we take the derivative of the position with respect to time, which gives us the velocity. The derivative of cosine is minus sine, and we get an omega, which multiplies our independent variable t. So we're going to get minus a times omega times the sine of omega t plus phi 0. And now, if we want the acceleration, we need to carry the kinematic ladder one step further. So we want to take the derivative of the velocity with respect to time. That gives us the acceleration. The derivative of sine is cosine. We get another omega out in front, so we get minus a times omega squared times the cosine of omega t plus our initial phase, phi 0. Now, we are looking for the maximum acceleration. We have an expression for our acceleration at any time t, but when is this going to be a maximum? Well, cosine here can have any value between +1 and -1. Okay, so we can take this to be 1 and we recover our maximum acceleration, and we get that the maximum acceleration is going to be equal to a omega squared. All right, but we don't know what omega is, so we need to look back at our given information and see if we can get at this omega. And it says here that the period of the oscillation is 1.5 seconds. So we need to go from period to angular frequency. And so we have t is given, t equals 1.5 seconds. And we know that the frequency is equal to 1 over t. And we know that omega is equal to 2 pi times the frequency. So we get that omega is equal to 2 pi over t, or I guess that's all we need, right? We have an omega, we have t, and that gives us an omega. So now we just need to combine these three equations, 1, 2, and 3, right? We have 1 which depends on ax max, we have 2 which depends on omega, and here we have omega which depends on t. So let's go ahead and combine those. We're going to get the amplitude A times omega squared, which is 2 pi over the period squared, divided by g, and that is going to give us mu sub s. This is returning us to equation 1 here. So last up, we just need to put in some values. This is equal to 0.4 meters, that's our amplitude, divided by 9.8 meters per second squared, that's g, times 2 pi divided by the period, which is 1.5 seconds. All of this guy gets squared, which gives us a value for the coefficient of static friction, which is 0.716.